Hello, everyone, and welcome to the eighth session of the International Workshop on Sports Biomechanics. Today, we have the international resource person, Ms. Kanisha Vincent. It is my honor to introduce her. She is a professional performance analysis and a testing officer at the Elite Athlete Wellbeing Unit of the Sports Company of Trinidad and Tobago. She had done MSc in sports performance. In her degree, she covered applied sports biomechanics, applied sports psychology, and applied sport at the University of Portsmouth. She recently opened her own business called Sweet for Science, which is geared towards helping athletes and individuals have a better relationship with assessment. With these words, I would like to request Ms. Kanisha Vincent, ma'am, to start her lecture. Ma'am, please.
Hi, good morning, everyone. Yes, my name is Kanisha. I'm from Trinidad and Tobago. I just want to say thanks for having me here with everyone. Thank you to Pranav and Shrikant for the introduction to HVPM as well. They gave me a bit of a background to the institution, and I'm really pleased to be here and to be delivering this lecture to everyone. Let me just share my screen, and then we can get started. Okay, good. Can everybody see the presentation?
Yes, ma'am, we can see your presentation.
Okay, great. So today I'm going to talk about the 3D analysis in sports biomechanics. And essentially, over the last decade, 3D motion capture has been an integral research tool used by biomechanists to quantify human and animal movements and to estimate kinetic parameters like joint forces, moments, and powers. And in sport performance specifically, motion capture aims at tracking and recording athletes' human motion in real time to analyze physical condition, athletic performance, technical expertise, injury mechanism, prevention, and rehabilitation. So, an overview of motion capture. We're going to talk about the hardware and software that's involved in mocap. What is motion capture modeling? How do we do motion capture? And then, what is motion capture outside of the gate lab? So, outside of all the fancy equipment, what does that actually look like? So usually when people talk about motion capture, we tend to think about the optoelectronic measurement systems, which involves the cameras that we see on the right-hand side and is basically a mixture of the hardware and software. These systems either track passive or reflective markers, so the ones that reflect light, or active LED markers, which are placed on different landmarks of the body to try to triangulate the 3D position in space. So generally, 8 or more cameras are necessary for full body capture through different marker sets based on the research that you've done, what you're trying to capture, and it usually comprises about 40 specific anatomic landmarks. Um, Actual systems can capture from 100 frames per second, well, which we refer to as FPS, to 500 frames per second. Although higher frame rates can be achieved by decreasing the image resolution, it may not always be relevant to sport and it may not be reflective of what you're trying to do. So frames per second, you can also swap that out for capture frequency as hertz. So 1 FPS equals 1 hertz. From these figures, a typical system would consist of about 12 cameras working at 200 hertz. And usually people refer to two major marketing systems or manufacturers, which would be Vicon and Optical. So yeah, we're going into optoelectronic measurement systems. Um, so these are more accurate than all the other systems, which is why they're usually used more often. They detect light, as we spoke about just now, and use this to estimate the 3D position of a marker via time of flight. So, time of flight is basically where sensors derive the range from the time it takes light to travel from the sensor to the target and then return. Um, the accuracy is dependent on a number of things. Those things would be the location of the cameras relative to each other, the distance between the cameras and the markers, the position that the markers are in, and the position of the cameras, the number and type of markers in the field, and the motion of the markers within the capture volume. Um, optical sensing encompasses a large and varying collection of technologies and image-based systems. So it's not only OMS systems that are used, and they also use, as we spoke about, a number of marker systems. So the position of the marker, just to elaborate, is estimated through the use of multiple 2D images of the working volume. The stereometric techniques correlate common tracking points on the tracked objects in each image, and they use this information along with knowledge concerning the relationship between each of the images and the camera parameters to calculate the position of the markers. The markers, as we said, can either be passive or reflective. Sorry, passive or active. So the traditional optoelectronic mocap systems, we talk, sorry, there was an OptiTrack, it was Qualisys. So we spoke about Vicon and Qualisys. There's also Elite, Motion Analysis, and OptiTrack. So these are considered to be the traditional apparatuses with which 3D motion capture is done. They all use retroreflective markers attached to the body surface and infrared strobes, combined with the camera lenses and sensors to collect 3D position of markers on the limbs, which are used to then compute the body segments and the joint kinematics. So just a bit of history. Motion capture is usually attributed to Dr. Julian Morris's research. The first optical mockup system per se. Um, so in terms of how it came about, he wanted to look at clinical gait data, what the qualitative and quantitative results would be, what the patient progress would be, and he wanted to have that data available in comparison to normative data from other persons who weren't um, struggling with any gait related issues. And he also wanted to increase the confidence in physiotherapy and surgical intervention. So, generally, motion capture analysis and data collection protocols, measurement precision, and data reduction models have been developed further to meet the requirements for the specific settings that they exist in, be it the clinical setting or the performance setting. For example, the sport assessments generally require higher data acquisition rates because of the increased velocities and that are needed to be examined as opposed to the normal walking as for like the gait trial with Dr. Morris. In virtual reality applications, so outside of sport, real-time tracking is essential for a realistic experience of the user. So the time lag should really be kept to a minimum, which means that they also need higher capture rates. So, years of technological development has resulted in many systems, and they can be categorized in the mechanical, optical, magnetic, acoustic, and inertial trackers. The human body is often It's often considered as a system of rigid links connected by joints, and human body parts obviously are not actually rigid structures, but they're usually treated as this or as such during studies of human motion. So the hardware. Um, Under hardware, we'll discuss the setting up of the cameras and the calibration of the system. So I don't know if you all can see in the photo here. At the top of the picture, there are a number of cameras around the room, and they all focus on the treadmill. Because more likely than not, in this type of setting, you're doing gait analysis with markers on the lower half of the body and possibly the trunk. They're all facing downward because the person will be on the treadmill at the bottom of the room. There's some cameras at the back of the room as well. And then there's the computer system in front. It's all connected by wires, and the information is fed through the computer. And then, we load them to CTD files. So the setup involves the placement of the infrared cameras in sight of the target area, and the target area would be the treadmill, and they're at a height that is most relevant to the capture markers and where those will be placed. Um, as it was mentioned before, the number of cameras that are set up is determined by the complexity of the movement that they'd like to capture, and as a result, the marker set, the positioning of the markers that we went over, and the kinematic and kinetic parameters of the action that we'd like to study. Um, in terms of calibration, we'll follow up on that a bit in the next slide. But the calibration basically maps the space and provides dimension to allow the action that will be studied to take place in the field of view, which is just like the treadmill area there, and be recorded with meaning in the system. Okay, so hopefully I can play my video here. On your left is a calibration wand from Vicon. Oh no, I can't play the video. Okay, hold on, give me 1 second. Let me see if I can share in a different way to play the video. Okay, so I'm sharing my entire screen to try to play this video for you guys. Okay, can you see it?
Yes, ma'am. Can we
Okay.
can we make it full screen?
Yeah, let me actually just,
Slideshow, slideshow.
yeah, I'll fully slideshow full screen as well.
Yeah.
Um, where is it? Slideshow. Okay. Okay, good. So as you can see in the video here, he's basically calibrating the space, and you really want to get every single part of the space that you want to have the captures camera, the camera's capture, sorry, visible on your system. So you need to make sure that you get all of the space within the area, and your software program would let you know how much of the space is covered. Okay, good. Right. So that's usually how you calibrate. Sometimes you have a setup where you place the calibration tool within the space and allow the cameras to capture that first, and then you use the wand to capture in the space. So some considerations of the optoelectronic measurement system is that they are fixed cameras. They can't really be moved outside of the lab area, and the capture volume is really dependent on the number of cameras and the field of view of each of the cameras. The largest range that has been measured with OMS systems was 824 meters squared, which was obtained with a Vicon MX30 measurement system, and 24 cameras are required. So I can imagine that the number of cameras used, especially 24 in this scenario, would present some significant practical difficulties, especially with cost, how portable they would be, the calibration of such a large area, the synchronization of all the cameras, the labor that it would take to get the cameras there and then to set them up. The line of sight is also an issue with OMS systems. The data output sometimes is interrupted when the camera loses sight of the markers, and the systems are highly sensitive to alterations in the setup as well as background light. So if it is that you accidentally shift a camera, then more likely than not you'd have to recalibrate your system. And if you are working with a very large system, that can present some problems. So for software, we're going to talk about what the software output would be. Software is generally dependent, or the software that you choose is generally dependent on your needs as a researcher, what you would like to, what information you'd like to get out of your assessment. The integration of third-party systems is possible with software, and there's customization of reports depending on the type of system that you go with. There's also quick processing options, also depending on the type of system that you go with. We'll speak about software a little bit more where we go into the main software companies or packages that are used in 3D biomechanics. As for modeling, so once you've done the calibration, once you've done the setup, then you've done the calibration, you've done your marker set research, then you'd be looking at modeling or creating a model. So, what is a model? So, a biomechanical model basically represents the physics of movement for human movement, um, in particular, the mechanical properties of the human body. And in many ways, biomechanical modeling deconstructs the science of human movement to address topics such as injury and performance. So 3D models represent a physical body using a collection of points in 3D space, and these are connected by various geometric entities such as triangles, lines, curved surfaces, etc. Why is a biomechanical model needed? So biomechanical models, as we said before, do help to deconstruct human movement. They help with injury prevention and injury feedback information, as well as recovery and then follow up participation and return to play. They also help to improve or give information that can help to improve performance by breaking down the basics of the movement. So biomechanical models, they'd be utilizing the software programs to realize multi-body mechanics. So we can be able to see those in real time. So these either which turn either they use either the D'Alembert principle, which is the realization of balance of power considering static and dynamic forces, or the Lagrange function, which is a system that is completely described by the energy of movement and the potential energy. So when it comes to planning a model, this is usually dependent on what you'd like to look at as a researcher needs, as well as if such a model was already available to you. So if it's done before in science and you'd like to repeat that, you'd like to look at the same thing, more likely than not, you'd go into the research and determine what your model would be. So there are some models that are available already, and we'll discuss those a bit later on. So just to elaborate, a model is a mathematical relation that allows the foreseeing behavior of the systems that has been modeled, given some known inputs and parameters. So once we know certain things, we're able to understand how a model would behave and in turn how human movement would behave in a particular situation. So how to apply modeling to human motion? So first we need the inputs, which are the markers and trajectories, and we said they can be either passive or active. We need model parameters or inertial parameters. So we need to know what our model can and can't do, and we need the output, so what we are looking at. So body segment inertial parameters are necessary parameters to perform dynamic analysis of human movement. And as these cannot be measured in a non-invasive way, they're classically estimated using anthropometric tables. So you'd really need your anthropometric tables to feed back in the type of model that you'll be using. Personalized BSIP or body segment inertial parameters can be estimated using identification techniques based on dynamic modeling of the body and experimental data about a motion and external reaction forces. So planning your model. First, as I said, you need to know what the purpose of the model is. Then you move on to which segments do I need to look at. You need to know what kinematic parameters do I need in the model. What kinetic parameters do I need in the model? You need to draw a free body diagram describing the rigid segments, describe the segment origins and orientation, and then define marker positions or placement. And once the research question or the hypothesis has been defined, your next step is defining the marker set for your model. The basic kinematic parameters would include the displacement or the distance, the velocity, both initial and final velocity and speed, acceleration and time, and their their combination in a complete trajectory. So those are the parameters that you need in order to develop your model. Um, Kinetic parameters, or also called low-level control, these refer to the control of individual muscles and forces. So we know that kinematics seeks to explain a movement without considering what causes it, and kinetic parameters is the forces or the low-level controls. For instance, or just for an example, when you throw a ball in the air, kinetics explains the friction that causes the throw, and kinematics explains the acceleration, the speed, and then the final position of the ball when it falls to the ground. The kinematic parameters you'd be measuring for something like you'd be measuring things like shoulder horizontal abduction and adduction, horizontal pelvis and upper torso rotation, or wrist flexion, like you'd see in an overhand handball throw, or possibly a cricket ball in action. So, in this specific context, kinetics examines the forces acting on the body during movement and emotion with respect to the time and the forces. Um, if an analysis of a penalty kick in football is done, for example, the kinetic parameters will include the force that's being applied to the object in order to create the displacement and then score the penalty try, hopefully. So for model marker sets, um, the considerations that we'd need to look at are the number of markers to use, the marker position that will allow for the meaningful anatomical reference frames to describe the motion. So if you're going to look at lower body movement, then you need to possibly have your shank, you need to have your leg or your thigh, and more likely than not, you need to have the foot marked as well. The minimum number of markers for segment definition with 6 degrees of freedom is three. So you do need three markers at the very least. And hinge joints or ball and socket joints require a group of three markers. So, for example, if you were to use the shoulder, you'd need three markers to determine where that joint is. And these would usually surround the joint to describe the connection. So you want to avoid the landmarks with excessive skin motion. I know that we all know what it looks like when somebody jumps per se, and the thigh tends to move quite a lot. So if you were to do analysis on power, also included like a force plate, you wouldn't want to put a marker on the thigh just because that marker would shift around a lot. And the aim for you'd like to aim for easily palpable landmarks, so like the lateral malleolus or the greater trochanter. And what's an easy hack is to also include below your markers, like use an actual colored marker and mark the spot that your marker would need to go at. That would help if a marker was to fall off in an assessment and you'd need to put it back in the same place. So you have like an easy way to know exactly where that marker was. For certain assessments where you have people doing a longer term kind of movement. So you'd have somebody running on a treadmill, for example. You do need a room that is cool enough so that the markers don't slide off their body, or you use extra tape or anything that would help keep your markers in position. You want to make sure that the markers are easily repeated, and the landmarks that you use will help you with that. And you also need to think about the anthropometric data, and you'd like to avoid collinearity because you don't want to see your markers reflecting the same thing. Okay, so we have two examples of model marker sets in this picture. On the left, we have a marker set for the back arm and shoulder, and on the right, we have a lower body marker set. On the left, I believe they also included AMG machines, and these are reflective markers. On the right, these are also reflective markers. You have some marker clusters around the thighs. These do help your markers to remain in place, but they are still very tricky depending on the motion that you're studying, the movement that you're studying. Again, some marker sets we have on the left. These are active marker sets. You can see in the little circle here that these are lights in this triangular space here. And on the right side, these are also active marker sets because this is light coming out of the marker as opposed to being reflected off the surface. So just to go over that, passive marker systems use markers that reflect light back to the sensor, and active systems use markers that contain the source of light for the sensors. The benefit of active markers over passive markers is that the measurements are usually more robust, but the active markers do require additional cables and batteries, which then limits the freedom of movement of the athlete. The sample frequency for active markers is usually lowered when multiple markers are used because each individual marker needs a distinguishable frequency that it can be identified by. Reflective markers or reflective systems, they use infrared light, so light that can't be seen by the human eye. Well, the cameras use the infrared light. And these lights are mounted around the camera lens, as we saw in the cameras earlier on in the presentation, um, along with the IR infrared pass filters, which are placed over the camera lenses, and they measure the light reflected from the markers back to the camera. Um, Optical systems based on pulse LEDs measure the infrared light emitted by the LEDs placed on the body segment. In addition to that, camera tracking of natural objects without the aid of markers is possible, but it's generally less accurate. It's largely based on computer vision techniques for pattern recognition, and it often requires high computational resources. The structured light systems either use lasers or beamed light to create a plane of light that is swept across the image, and then that gives the analysis of the image and the area. These are more appropriate for mapping like applications than dynamic tracking of human body motion. So applications that can be used to create a model. So there are various applications that can be used for model creation. I'm just going to go over a few of them here. We have Matlab, Matrix, we have Python, we have CMotion, Visual 3D, which most of us may be familiar with. TFlow by Motec, Labview by National Instruments, the Motion Monitor, OpenSim, and Vicon ProCalc, which is one of the most robust systems that I use with this type of 3D motion capture. So just going to go through the different types of software and just give some background as to what they would track. So Matlab is a programming platform and it's designed specifically for engineers and scientists. Um, the heart of Matlab really is the Matlab language, and it is a matrix-based language which allows for the most natural expression of computational mathematics. Um, Matlab is a very powerful tool and it has a large community. It's a script based language and it involves a steep learning curve. So you do need to do a lot to be able to operate a Matlab system. So this is actually a video. And once again, I'll share my screen to show you all. It's a very short clip, and this is gate analysis within Matlab. So it just shows you the tracking of the markers and what it usually looks like in that system. Okay, great. Next, we have Python, and we probably have all heard of Python before, and it's general purpose. It's a general purpose system, and it involves a lot of high-level programming language. And you usually use Python for developing, or you can use Python for developing biomechanical models. Um, PyCGM2 has been developed and written with Python. It has a mid-sized community and it's also a script-based language. Um, there's also a direct integration between R and Python, and you can run your R code from within Python as well. Um, R is a programming language for statistical computation and graphics that can be used to clean, analyze, and graph your data. It's widely used by researchers from diverse disciplines, and it is used to estimate and display results by teachers of statistics and research methods. So in this slide here, you can see that there's some model creation down at the bottom. And specifically, I took this from the Maksudi et al. Research paper, and they used OpenPython software to analyze the 3D biomechanics of quadrupedal animals. This specifically is used with, or is information from the rats that they used. Then we have C-Motion Visual 3D. Visual 3D is probably one of the most popular 3D biomechanics software platforms at the university level. It's what I learned 3D biomechanics on, and it is specifically a biomechanics analysis toolkit. It is a Windows application, which I guess makes it more accessible, and it provides the calculations needed for kinematics and kinetics. It includes the latest mathematical techniques for optimizations, signal processing, and filtering, as well as inverse kinematics, complex biomechanical modeling, forces, and force structures. So, if you do want a go to system, I think that Visual 3D really has everything when it comes to biomechanics and biomechanical assessments. Um, TFlow from Motec. It is an enhanced visual programming tool for interactive and immersive application development. That is, sorry, TFlow. And it displays the virtual scenes alongside a treadmill, so you get to see what's happening while you do your assessment. And it enables rapid prototyping for your research. So it is that quick feedback, quick flow that we spoke about earlier. Additionally, it can, yeah, so you can use integrated scripting to advance the sophisticated application development with TFlow. And it also includes human body models as part of the package. Once again, this is a video that I have. So yeah, this is directly from the Motec website, and it is the setup of this particular system. So it's very nice. It's also very expensive, and it's probably one of the ones that are that is easier to use, I think. But it takes a lot of setup. Labview by National Instruments. This particular software allows for, or it offers a graphical programming approach, and that helps you visualize every aspect of the application. It has a mid-sized community, and it also has quite a steep learning curve, as with math roots. Um, on the slide here, this is data from a study by Cazzola et al. From 2013, and they used Compact Rio and Labview to look at or to measure and analyze biomechanical stresses in machine and live scrummaging in rugby. So in rugby 15s, they did against the rugby machine. I think you can see the machine on top there, and then one team against the next, or one group against the next, and what the differences would be like as they completed the movement. There's Motion Monitor, and Motion Monitor provides real-time solutions to a wide range of applications, and that involved the study of human motion. And Motion Monitor was designed to really analyze all aspects of human motion. In sports biomechanics, Motion Monitor will both monitor and enhance performance, track and animate sports objects for golf, batting, pitching, tennis, bowling, and biking. So those are the two applications of Motion Monitor. It also provides biofeedback for exercise to enhance visual responses. So you get feedback for hand-eye coordination, movement patterns, and it uses audio feedback as well. OpenSim is another system. It provides easy to use software for modeling, simulating, controlling, and analyzing neuromuscular systems. It is freely available. It's very easy to use, and it has a, a wide offering as a software system that allows users to develop models of musculoskeletal structures and create dynamic simulations of movement. And lastly, we have Vicon ProCalc. Um, ProCalc is a visual application for creating the custom kinematic models, the variables, and event calculations using a simple wizard-based system. So for the system, you can just load in your CTD files, you can create new calculations, and you can then visualize outputs in an integrated 3D workspace. um, Variables and events that are calculated in ProCalc, they can then be written back into CQD files, which is great, and they can also be exported to Excel. There are some readily available models. As we spoke about earlier, I was going to talk about the models that are readily available, and these can be used with Vicon. Um, Certain models can be applied to different activities, the ones that already exist. Examples of these models are the conventional gate model, or plug-in gate found in Cadabra in 1990, Davis in 1991, and the Oxford foot model found in Stemmons in 2006. You can also find a library of available models on the Vicon website. So if you go to their website, there is all the models there that are available for you to use. So it's important to define joint centers for specific movements. And what we're going to look at is defining the joint center for the hip joint. And you can either use the regression method or the functional method, namely the score or SAR method for defining joint centers. So the regression method will be used to estimate the location of a virtual joint center. Um, the joint regression model for two-way data, it assumes a linear relation between a continuous response and column effects, and standard methods for fitting the model condition on estimates of the column effects, but including column effects as covariates in the model results in a nonlinear estimation problem. So there are different types of regression analyses. These are linear regression, logistic regression, polynomial regression, ridge regression, lasso regression, quantile regression, Bayesian linear regression, and principal components regression. Regression analysis is a reliable method for identifying which variables have impact on the topic of interest. And the process of performing a regression allows you to confidently determine which factors matter most, which factors can be ignored, and how these factors influence each other. So with regressions, we usually look at dependent variables, and that is what you're looking at. That is the factor that you want to see the effect in, as opposed to independent variables. In the model, these are the factors that you hypothesize will have an effect on your dependent variable. So you hypothesize that kicking a football will apply a certain amount of force, and that is your dependent variable will be the force, and your independent variable will be the kick itself. So the second method is the functional method, which uses multiple frames of data where the joint of interest is moving. So it's in motion as you calculate. And functional methods identify joint centers as the center of rotation of two adjacent movements during an ad hoc movement. The methods that have been used for functionally determining hip joint center in gait analysis have revealed advantages compared to predictive regression techniques. So, functional methods um, have shown advantages for their use as compared to regression. SCORE stands for Symmetrical Center of Rotation Estimation, and SAR is Symmetrical Axis of Rotation Analysis. The SCORE method only locates the joint center, while the SAR method only locates the joint axis. So we'll talk a bit more about the regression versus the functional method. Um, In a lecture delivered by Jacques from Vicon on optical motion capture, the differences in software output when calculating hip joint centers and axis of rotation are explored. Um, these images are taken directly from that video. It was posted on a YouTube channel uh, entitled Stuart McKellen Naylor, and the video is Vicon Motion Capture Hardware, Software, and Modeling. So if you'd like, you can go back and look at that video. Um, it is part of a lecture series on sports biomechanics, and the focus is on hip joint center and the difference between the regression method and the functional method. The Davis method has been implemented into the conventional gait model, and we see the Davis method here. So you see the differences with where they estimate the hip joints to be, um, and you see the difference between each method, as well as when they compared at the bottom, how they they differ in where they place the data points. So the Harrington and Hara method, they're also systems that can be used to calculate hip joints, but they're not on the slide here. Um, the thing is, seeing the hip joint center being calculated in different locations based on the method that you use, it really should always make you think about, am I using the correct modeling method, and how will the modeling method that I've used affect the model outputs? Okay, so we've talked about optoelectronic measurement systems for quite a while, but that's not all when it comes to looking at 3D biomechanics. So some other systems that can be used for 3D motion capture. One of them is the electromagnetic measurement system, which utilizes transponders and base stations. Um, it has a larger capture volume than the OMS, but it is less accurate. So, electromagnetic systems find the unknown position of measurement transponders by means of time of flight as well. But they use radio waves traveling from the transponder to the base station, and that will then help to triangulate the position of the markers in space. The sample frequencies are generally low, and GPS GLONASS EMS system is one example of this. It had a zero point zero 0.04 meter accuracy in a range of 15,000 meters squared. So it may not be the most accurate system that can be used. It's also a satellite-based system. And in one of the papers that I looked at, Van de Kruk in 2018, they did a systematic review of the accuracy of human motion capture systems for sport application. In their research, each EMS system had a lower frequency than the worst performing optoelectronic system. So they're not necessarily the best. They do suffer from sensitivity to ferromagnetic material in the environment. So that'll be based on your setup and how and where you do set up the system. This then decreases the accuracy of the data, as well as when the distance between the transponder and the base station is increased, the noise increases, and the quality of the system then also decreases. Um, As I stated, EMS generally has lower sample frequencies, and yes, GLONASS is a satellite system. They also have local position measurement, which is a different type of system, and these also contain base stations. They're positioned throughout the area that you'd like to look at, and they have transponders that are worn by these subjects. The main base station first sends a trigger to each transponder, and then each transmitter sends tagged electromagnetic waves to all other base stations. So it's like a sequence of transmissions. The same, it's like the same for the GNSS, which is the GPS glance that we talked about. It does need at least four base stations to receive a signal to determine 3D position of the transponder, and it also uses time of flight. The satellite system can really only be used outdoors because it uses satellite, but the LPM system, it can be used indoors because it sorry, yeah, it can be used both outdoors and indoors because of the type of system that it is. And the accuracy of this specific system, the LPN, um, is presented as 0.23 meters for a dynamic situation, so 23 kilometers per hour, in an area of 3,840 meters squared. Another system that falls under EMS is the radio frequency identification, or RFID. It is a wireless non contact system which uses electromagnetic waves and electromagnetic fields to transfer data from a tag attached to the object to the RFID reader. And there are two types of tags for RFIDs. There are the active tags, which actively emit radio waves, and passive tags, which can be read only over short ranges since they are powered and read by magnetic fields or induction. Um, in sports, the RFID system was tested at an indoor basketball field. The accuracy, or the field was 420 meters squared. The accuracy was 0.19 meters, and factors such as attenuation, crossing paths, the signals crossing paths, and interference from other RFID tags. RFID readers and different RFID devices can affect the communication between the tags and the RFID reader. So those are the drawbacks for the RFID system under EMS. Then we have image processing systems. Um, IMS is generally more accurate compared to AMS, and it also has an improved range of motion when compared to the optoelectronic measurement systems. It is a vision based system and uses optical cameras and computer vision algorithms to produce the work that you need. Markerless systems are available, and marker tracking, the ones that do use markers, use visible light for humans as opposed to OMS that uses infrared light. It is not easy to perform image recognition in real time in this type of system, and it might require expensive, high quality, and or high speed cameras to be able to capture the high speed human motion that we would like. Accuracy is dependent on the environmental setup, so how you set up and where, the position of the camera in relation to the object trajectory, and the number of cameras in the field. Um, it's currently outperformed by the OMS or the EMS, and the maximal range is is small, at least compared to the EMS. So, continuing on under image processing systems, you have the model-based system and the feature-based system. So, the model-based system uses a 3D model of the tracked object. It is generally hard to use in unknown environments, and it restricts camera motion. What I mean by that is the model-based system needs additional information, such as the 3D models and the environment. Um, if it doesn't have this, it doesn't have the information that it needs to give you the data that you're looking for. Um, Feature-based systems, they use interest points in the frames to track the object. And there are two types of feature-based system tracking, marker tracking and markerless tracking. The marker tracking uses known markers, and markerless tracking focuses on tracking 2D features such as corners, edges, and textures. So marker tracking eliminates, or markerless tracking, sorry, eliminates dependency on the prior knowledge of the environment that you'd have with the model-based system, and it extends the operation range. So in sport, marker-based feature tracking has been applied in the collection of kinematic data on ski and snowboard, on a ski and a snowboard track, where the accuracy of the system was 0.04 meters, and this was obtained in a 2,500-meter square range. Liu et al. In 2009, they mounted a panning camera to the ceiling of um, uh, a building that speed skaters use to track short track speed skaters during a match. And using a color histogram of the skaters, they obtained an accuracy of 0.23 meters in an area of 810 meters squared. There are also ultrasonic localization systems. As we know, ultrasound is stealthy for the human ear as compared to sound, so you won't really be able to hear ultrasound. Um, Mostly used in the short range measurements, because ultrasound doesn't travel as much as sound. It determines the position of an object by means of time of flight of the ultrasound wave traveling through the air. These systems are called acoustic measurement systems, and the range, as I said, is limited compared to sound. The problem with ultrasound is that the directionality of ultrasound can be a disadvantage when working with dynamic measurements. We also have inertial sensor measurement systems, and these consist of an accelerometer, a gyroscope, and often a magnetometer. By combining the information from the accelerometer, so the gravitational acceleration, data from the gyroscope, which is the rotational velocity, and the orientation from the magnetometer, the orientation of the device can be determined. So the magnetometer is usually used to track the magnetic north, to then determine the heading of the IMU. The IMUs are commercially available, and they are capable of detecting very rapid movement, and they're also non-invasive, which does sell people on their use. The system is susceptible to measurement errors due to nearby metal, and the sensor fusion algorithms are sensitive to linear accelerations. As a standalone system, the device cannot determine its global position, which limits its application to sport. But the IMUs don't have a base station, and that means that they're more mobile than other measurement systems. So now that we've spoken about all these systems, then how do we do system selection? So Van der Kerk, because they did a systematic review, they looked at all the systems and they wanted to know what or how one would go about selecting the system. So in the A box is basically all the systems plotted along both accuracy and range. And in the B box gives you the analysis of how you then go about choosing your system. So the graph B can be divided into four sections. which then defined by the minimal measurement range and the minimal accuracy range required of the research setup in question. So the upper left area would be systems that have a small range and low accuracy, which they refer to as not applicable. So these would not be useful for sport. They also had the lower right area, which contains systems that satisfy the specific requirements of both range and accuracy. So these were generally viewed as applicable and could be used. The lower left area uh, were systems that met the accuracy requirement, but they didn't have the required range. And these are referred to as low in range systems that didn't have the range to utilize a larger space. And the upper right area would be systems that had the range but didn't have the right accuracy. So these are referred to as low in accuracy. So sometimes, none of these systems in a chart would meet the volume accuracy requirements. And it is possible to combine systems from the low in range and low in accuracy areas via sensor integration, like we spoke about. And the data from the different measurement systems can then be combined to determine one variable. For example, by combining IMU data and GPS data, the high sample frequency of the IMU is combined with the position data of the GPS to compensate for integration drift of the IMU. This was looked at in Brody, Walmsley, and Page 2008. So a fusion motion capture system requires a fusion algorithm to combine the data of both measurement systems. For example, like a Kalman filter or a comparative filter. But yes, so that would really be it on the 3D biomechanics in sport. These are all my references. There are quite a lot of them. And if anybody has any questions.
Thank you so much, ma'am. There was very informative that many things about this 3D motion analysis was not known, and there are a lot things we have learned today. There is one question from the online participants, that is, how can we use this 3D analysis in during the match, during the competition?
So using the 3D analysis during the competition does depend on the type of system that you'd like to use. It would have to be something that is markerless, because you don't want to restrict movement during a match. You want athletes to be at their best competitive form during a match. So you would really need a system that does not use markers, as well as has a high accuracy and high frequency you need to be able to capture. And it also depends on where you're able to position your sensors. I haven't seen, other than for, let's say, track and field, where they examine certain track events at the Olympics. I haven't really seen the use of 3D motion capture in, let's say, team sport matches, to be honest.
Thank you so much, ma'am. There is one more question from the offline participant.
Good morning, ma'am.
Good morning.
Ma'am, my question is, what is the base wall color for optical mocap system?
Sorry, can you repeat?
What is the base wall color for mocap system, optical mocap system?
Oh, it's usually black. So it's usually in a very dark room. You either have like curtains or something to stamp out all the light. because if you have light in the background, it does appear as a marker and it kind of sets your calibration off.
We can use the light color, ma'am, if we are using
Sorry.
light color, white color.
Yes. But if you need to turn off all your lights as well.
Okay. Thank you, ma'am.
Good morning, ma'am.
Good morning.
My name is Rituraj. I am in BP third year. So my question is to you is that you told about musculoskeletal modeling, uh, in which we measure a different body segment of an athlete and uh, try to build a model in software, and that software uses different type of workout and different techniques that is not prescribed by coach. As a biomechanist, you used to develop a new technique, you give that technique to that model. So my question is to you is that what type of techniques we use to measure body parameter segment, that is BPS? What type of technique we use to what kind of software which is freely available to build musculoskeletal modeling?
The ones that are freely available. So the one that is freely available to do the musculoskeletal is the OpenSim.
And my another question was, ma'am, what kind of technique we use to measure body parameter segment?
What type of method we use to measure
Body parameter segment.
within the application?
Yes, within the application, we use to measure our mass of the bone and length of the bone to the computer to build a model. What
So
kind of
your
technique?
markers, sorry, your markers would usually help you determine that through the system, the software system that you use, in addition to the anatomical references that you'd have. So the anatomical norms and the marker sets in the system would help you determine those things.
Ma'am, isn't two techniques cadaver method and immersion method?
Yes.
That's okay. Okay, ma'am. Thank you, ma'am.
Hello, ma'am. This is Shalini from BPS final year. My question is, while preparing a biomechanical model for sprinting, is there any perfect angle or average angle between the joints? Is there any perfect angle that is to be considered for the best movement of athlete like that?
For sprinting, you'd want to have a system that sees the athlete from all angles. You definitely want to see them from the side. So maybe 8 cameras, if you're using that kind of system, that would be useful for you.
Okay, ma'am. But I just want to ask that what should be the average or the perfect angle between the ankle joint and the knee joint? What should be that is considered for the best movement of the athlete?
The perfect
Is
angle
there any specific angle that is to be
for the
considered?
for the camera.
Yeah, for camera. Yeah, that
I'm sorry, I don't have the specific number for you.
okay, ma'am. Okay, thank you, ma'am.
Any other questions from the any other questions from the participants? I would like to announce that to deliver this session, to conduct this session, Miss Kanisha have to wake up at 4 in the morning, and it is her dedication about sports that she woke up in the morning to conduct this session. And with a huge round of applause, we will just applaud her. Please. On behalf of organizing committee, I would like to thank Ms. Kanisha Vincent ma'am for conducting this very good session, and we are hoping you ma'am to please visit India and HPPM once, so that we could have an offline session, and you will have the known how HPPM works and how it is. Thank you so much ma'am for joining with us.
Thanks for having me.
Thank you so much ma'am. It is an honor to have you ma'am. Thank you. Next, we will have a closing ceremony, and for that closing ceremony, I will give the mic to Miss Dr. Anita Gupta, ma'am, and she will be conducting the closing ceremony of the workshop. Hello.
I'm Khandagle, organizing secretary of this workshop. Wholeheartedly, I welcome you all on closing ceremony of this 3 days international workshop on sports biomechanics, organized from 27 April to 29th April 2022. This workshop was conducted in blended mode, and we have got a remarkable responses from the participants of off the line and on the line as well. Now, I request Dr. M.L. Khandagle sir, organizing secretary, to present the report of the workshop. Sir, please.
धन्यवाद. गए लास्ट आखिरी के 3 दिन से हम यहाँ पर लगातार स्पोर्ट्स बायोमैकेनिक्स इस वर्कशॉप के ऊपर चर्चा कर रहे हैं। और मुझे लगता है कि ये जो आखिरी का समय जो यहाँ पर अपने यहाँ पर हुआ अभी, जो इंटरनेशनल रिसोर्स पर्सन यहाँ पर जुड़े, और लास्ट जो रिसोर्स पर्सन यहाँ पर कनिष्ठा मैडम यहाँ पर हमसे बात की है, ये जो 3D एनालिसिस है, ये 3D एनालिसिस काफ़ी एकदम हाई लेवल का पूरा स्ट्रक्चर है, क्योंकि इंडिया में केवल लैब जो अपना स्पोर्ट्स अथॉरिटी ऑफ इंडिया है, जहाँ पर इंटरनेशनल एथलीट जो होते हैं, तो उन्हीं के लिए यहाँ पर वो उनका एक स्ट्रक्चर वहाँ पर बना हुआ है। बाकी जो 3D एनालिसिस जितना भी स्टडी होता है वो पूरा फॉरेन में उनका स्ट्रक्चर, क्योंकि बहुत बड़ा स्ट्रक्चर इसका होता है, क्योंकि ये वीडियो पूरा लगा हुआ रहता है, सेटअप लगा हुआ रहता है, क्योंकि अगर एक ट्रैक का अगर हमें सेटअप करना है तो काफ़ी बड़ा सेटअप उसमें लगता है। और ये सेटअप के साथ साथ मेंटेनेंस और ये सब कुछ जो है हमें अभी इंडिया में अभी उतना प्रोलॉन्ग अभी डेवलप अभी नहीं हुआ है, लेकिन अभी धीरे धीरे हमारे इंडिया में भी इसका डेवलपमेंट शुरू हो चुका है। प्राइमरी लेवल पर, बेसिक लेवल पर काफ़ी सारे जो एथलीट है, अभी बाहर जाने से अच्छा है कि हम यहीं पर इंडिया में उसका भी एनालिसिस अभी यहाँ पर होने जा रहा है। ये जो 3D एनालिसिस है उसमें काफ़ी बड़ा मटेरियल्स, काफ़ी सारा स्ट्रक्चर्स इससे लगता है। तो ये कनिषा मैडम ने हमें जो बताया तो हमारे काफ़ी लेवल पे कब ऊपर जाता है, क्योंकि कहीं पर भी ये नहीं है, क्योंकि इसका स्ट्रक्चर एनालिसिस करते करते कौन सा एंगल कहाँ पर जाता है, क्योंकि उसके साथ सब पैटर्न उसके साथ जुड़ते हैं, फिजियोलॉजी, साइकोलॉजिकल जितने भी एस्पेक्ट्स हैं सब इसके साथ होते हैं, तो उसके कारण उसका स्ट्रक्चर जो है बदल जाता है। तो ये 3D एनालिसिस के बारे में काफ़ी शॉर्ट नॉलेज हमें यहाँ पर दिया है उन्होंने उनके हिसाब से, तो मुझे लगता है एटलीस्ट 25% तो भी हमें थोड़ा सा नॉलेज मालूम हो गए हैं। तो लास्ट 3 डेज में हमें जो वर्कशॉप यहाँ पर गए, तो प्रैक्टिकली ऑफलाइन जो वर्कशॉप स्पेशली जो यहाँ पर ऑर्गेनाइज हुए थे, जहाँ पर हमारे साथ ओपनिंग सेरेमनी में डॉक्टर प्रोफेसर विवेक पांडे LNIP इस महाविद्यालय वाइस चांसलर हमारे साथ जुड़े थे, इनके माध्यम से इस वर्कशॉप का उद्घाटन हुआ। उसी के साथ साथ वहाँ पर हमारे प्रेसिडेंशियल जो स्पीच है डॉक्टर अजय पाल उपाध्याय सर ने हमें अच्छा मार्गदर्शन किया कि इंटरनेशनल हमारा अचीवमेंट क्या क्या रहा है, क्योंकि ये इंटरनेशनल अचीवमेंट इसलिए हुआ है क्योंकि हमारे साथ इंटरनेशनल लोग यहाँ पर जुड़े थे, तो इसलिए इंटरनेशनल अचीवमेंट भी हमारा काफी बड़ा अचीवमेंट इनके साथ रहा है। और इसी के आधार पर ये स्पोर्ट्स बायोमैकेनिक्स वर्कशॉप इस महाविद्यालय ने, इस संस्था ने काफी बड़ी मात्रा में इसको लेने का प्रयास किया था, और मुझे लगता है कि आज उसको 100% सक्सेस हुआ ऐसा मैं सोचता हूँ, क्योंकि प्रैक्टिकली ऑफलाइन वर्कशॉप जिसमें सबसे ज्यादा प्रोफेसर शत्रुंजय कोटे, इन्होंने प्रैक्टिकली काफी अच्छा गाइडेंस जो इंडिया लैंग्वेज, ओन लैंग्वेज में हमें काफी यहाँ पर बताया। तो जो ऑफलाइन और ऑनलाइन दोनों यहाँ पर जो पार्टिसिपेंट यहाँ पर जुड़े, उन सभी का जो ओपिनियन था कि ये सबसे बेस्ट वर्कशॉप यहाँ पर हुआ है। एक्चुअली ये वर्कशॉप प्रैक्टिकली होता है, तो ये प्रैक्टिकल वहाँ पर हमें उसका काफी सारा नॉलेज यहाँ पर मिला। उसी के साथ साथ डॉक्टर तनुजा राउत मैडम जो संत गढ़गेवा अमरावती यूनिवर्सिटी हेड ऑफ द डिपार्टमेंट है, इन्होंने भी अपना जो बायोमैकेनिक्स मदर इंस्टीट्यूट के बारे में बताया, तो उसके बारे में भी काफी सारा नॉलेज हमें यहाँ पर दिया है। दूसरा सेकंड डे डॉक्टर घई सर जो अपने यहाँ के संस्था के प्रोफेशनल जिन्होंने स्टार्ट किया, ऐसे हमारे घई सर जो आज HOD है, जो एग्जाम कंट्रोलर है LNIP में, तो उन्होंने भी बायोमैकेनिक्स के बारे में हमें काफी हिंदी और इंग्लिश बोथ लैंग्वेज में यहाँ पर हमें नॉलेज दिया है। साथ ही साथ स्पोर्ट्स अथॉरिटी ऑफ इंडिया जो डॉक्टर प्रवीण नायर बेंगलोर, इन्होंने काफी सारा जो अचीवमेंट कैसे होता है वहां पर कैसे एनालिसिस किया था, 2D मोशन में हमें कैसे एनालिसिस होता है, हमारा बॉडी का स्ट्रक्चर कैसे होता है, तो इसके बारे में जो नॉलेज देने का काम किया डॉक्टर प्रवीण नायर जो स्पोर्ट्स अथॉरिटी ऑफ इंडिया के हेड ऑफ द डिपार्टमेंट है बायोमैकेनिक्स के। और अगर आपने किसी ने देखा नहीं होगा तो सही में बेंगलोर में जाकर एक बायोमैकेनिक्स का जो लैब है बहुत अच्छा है और देखने लायक है, तो आपने देखना ही चाहिए। और वो यहाँ पर जुड़े थे, उन्होंने काफी अच्छा नॉलेज हमें दिया। थर्ड जो हमारा लास्ट में थोड़ा सा कम्युनिकेशन थोड़ा सा प्रॉब्लम, इलेक्ट्रॉनिक्स जो मीडिया हम जो बोलते हैं इलेक्ट्रॉनिक नेट एंड वाईफाई, तो उसका कम्युनिकेशन प्रॉपर ना होने के कारण हमारा जो ऑनलाइन जो यहाँ पर वर्कशॉप चालू था, तो उसमें इकराम हुसैन सर के बीच में काफी सारी कठिनाई हमें महसूस हुई, और लास्ट टाइम में उनको गूगल मीट पे ज्वाइन होना पड़ा, और उसमें काफ़ी सारा डिस्टर्बेंस, क्योंकि टाइम पे गूगल मीट ज्वाइन होने के कारण काफ़ी लोग जुड़ते गए और उनका किसी का वॉइस ओपन रहा, ये रहा, उसके कारण काफ़ी सारा डिस्टर्बेंस इकरम हुसैन सर के बीच में हमारे लेक्चर में हुआ। उसके बावजूद उनको भी ये थोड़ा एहसास हुआ कि ये मेरा जो लेक्चर हुआ वो प्रॉपर नहीं हुआ। उन्होंने उसके लिए जो उन्होंने मटेरियल तैयार किया था वो आपके सब ग्रुप पे डाला हुआ है कि कम से कम अगर वहाँ पर अगर प्रॉपर नहीं हुआ है तो कम से कम इस पीपीटी को या इस मेरे मटेरियल को आप देख सकते हैं। तो ऐसे डॉक्टर इकरम हुसैन इन्होंने भी अच्छा काफ़ी सारा जानकारी यहाँ पर दिया है। आज दोनों भी जो रिसोर्स पर्सन हमारे साथ इंटरनेशनल से जुड़े थे, मजी मुंबा और दूसरे थे हमारे अनिशा विंसेंट, इनको लाने के लिए जो सही में थैंक्स मुझे करना चाहिए वो स्पेशली थैंक्स मैं प्रणव चेंडके को करूंगा, क्योंकि इनके ही इनिशिएटिव से ये 2 पर्सन जुड़ने के कारण आज अपना एक जो वर्कशॉप नेशनल लेवल पे होने जा रहा था वो इंटरनेशनल लेवल पे चला गया। क्योंकि क्या है, 2 लोग अगर भी जुड़ते हैं तो काफी बड़े मात्रा में योगदान उसका होता है। तो संस्था का अपना हमेशा रहता ही है कि हमेशा आगे की तरफ आगे का सोचना हमारा काम होता है, आगे बढ़ो, सबसे आगे बढ़ो। तो सही में प्रणव चेंडके सर ने हमें ये काफी इतना व्यस्त समय होने के बावजूद उन्होंने अपना एक योगदान यहाँ पर दिया कि सर मैं और बात करता हूँ, लास्ट में हम दोनों काम ले सकते हैं। और उन्होंने काफी मेहनत करके 3 दिन से लगातार, जैसे ही स्टार्ट होने से पहले उनके साथ मीटिंग भी हो गई और सही में उनका कम्युनिकेशन बराबर हो रहा है नहीं हो रहा, ये सब बातें करते हुए लास्ट में ऐसा हुआ था कि एक रिक्वेस्ट हम लेकर गए थे कि थोड़ा सा ये प्रोग्राम थोड़ा सा अर्ली हो सकता क्या। तो वो थोड़ा सा उस समय एकदम चिढ़ गए कि आप क्या बात करें, इंटरनेशनल लेवल पे ऐसी बात करें, क्योंकि वो ऑलरेडी 4 o'clock में वहां से सेशन स्टार्ट करे और अगर हम और अर्ली करते हैं तो कितने बजे वो प्रोग्राम स्टार्ट करेंगे। तो इसीलिए हमने फिर जो है उसी समय में हमने इसको कंटिन्यू करने का प्रयास किया। और मैं स्पेशली श्री डिग्री कॉलेज ऑफ फिजिकल एजुकेशन के तरफ से और शारीरिक शिक्षा के विभाग के प्रमुख होने के साथ साथ महाविद्यालय की तरफ से मैं उनका हार्दिक हार्दिक आभार व्यक्त करता हूं। उसके बाद यहाँ पर जिन्होंने भी जितने भी यहाँ पर रिसोर्स पर्सन हमारे साथ जुड़े, उन सभी रिसोर्स पर्सन ने अपना यथा योग्य जितना भी समझाने का, वर्कशॉप में ज्यादा से ज्यादा योगदान देने का जो काम किया, मैं उनका भी महाविद्यालय की तरफ से आभार व्यक्त करता हूँ। साथ ही साथ आप लोगों को, मुझे लगता है कि यहाँ पर जो आज वर्कशॉप 3 दिन से लगातार स्पोर्ट्स बायोमैकेनिक्स इसके बारे में हम चर्चा करते रहे, तो मुझे ऐसा लगता है कि एटलीस्ट 50% तो भी स्पोर्ट्स बायोमैकेनिक्स क्या है ये तो कम से कम आज आपका 50% नॉलेज यहाँ पर मालूम हुआ। और ये सोच के साथ ये वर्कशॉप ऐसा सक्सेस हुआ, ऐसा मैं मेरी तरफ से सोचता हूँ। धन्यवाद मुझे यहाँ पर बुलाया।
Thank you so much, sir. Now, I request President of the closing ceremony, Dr. A.P. Upadhyay, sir, to enlighten us with presidential words. Sir, please.
Thank you, Anita Madam. Secretary of the institution and Director of this program, Dr. Madhuri Chenke Madam, Organized Secretary of this international workshop in biomechanics, Dr. Khandagale sir, Coordinator of this program, Dr. Anita Madam, Convener, our Assistant Professor, Pushpak Konde sir, Pranav Chandke sir, the guy who contributed a lot making our this national program international, and my dear students. Dear friends, our linkage, affiliation, connectivity definitely affect a lot. And dear friends, we cannot ignore, the scientific part for the personal and professional growth. And this is how we are always striving to have this type of program, seminar, symposium, convention related to different games and sports and fields are definitely meant to updation of our knowledge. I'll tell you, in our profession, lot of teacher is still they are presenting their outdated knowledge to the student. Why? Because lack of these symposium, seminar, and other these enrichment program. This is an enrichment program. This should be must. Without this enrichment program, you cannot imagine about personal and professional growth of the student. And I should tell you, this exposure is very important. These experts, those who presented ideas and concept of biomechanics before you, they were not different, they were like you only. They too have done BP, MP, MPhil, NetSet, and working in their profession, in our profession. And this is how to, with this concept only, our student, they could develop in same direction and can achieve same status and can enjoy same status we brought and we conducted this seminar. And I should tell you, responses of our students were overblaming. Some of the boys, the way they were asking question, they were putting question was very encouraging. And I must congratulate all the organizers, my students, for their participation. Definitely some of the students, when they were part of the seminar, they were thinking why they are, forcing us to become part of this seminar. Your keen interest definitely affect outcome of any things, We have to change our attitude to achieve a higher goal. Definitely these allied subjects, they are very important. Your participation, your keen observation, keen participation is very important. I'm very much thankful to this organizing committee, those who organized and brought this program for all the students. And I hope in coming time, they may prepare for some other, subject. So our student, they can enjoy and can update their knowledge. Since morning you are here, may not be enjoying what I'm talking, because whatever is presented before you, that was more important than whatever I'm summarizing you. Anyhow, here I conclude my presidential speech. Thank you for everyone for listening patiently. Jai Hind, Jai Maharashtra.
Thank you very much, sir. Now, I request Assistant Professor Mayur Kumar to propose vote of thanks.
Good evening, everyone. It has been such a wonderful opportunity for all of us to be a part of this international workshop on sports biomechanics, isn't it? Yes. On behalf of the organizing committee, I would like to express my heartfelt gratitude towards all the resource persons for their tremendous contribution for the international workshop on sports biomechanics. I present the profound gratitude towards Honorable General Secretary Prabhakar Rao Ji Vaidya, Tauji, for his blessings to organize the workshop. I extend my thanks to our beloved principal, Dr. Ajipal Upadhyay, for his visionary guidance to make this workshop remarkable. Thank you, sir. Now I would like to present the gratitude. Thank you, ma'am. Now I would like to present the gratitude toward the workshop director, Dr. Madhuri Chenke ma'am, Secretary HVP Mandal, Amravati, for her encouraging guidance to make this workshop remarkable and impacting. I also extend my gratitude to organizing secretary for his extraordinary efforts for organizing this tremendous workshop. I also extend my thanks to workshop convener Dr. Anita Gupta ma'am, in charge MPIT program DCP HVPM, for her continuous efforts and hosting the closing ceremony. Thank you, ma'am. We are also grateful to Mr. Pranav Chenke for introducing us to international entities as a resource person, which indeed left an impact on this workshop on sports biomechanics. Now, I would like to thank our workshop coordinator, Pushpak Khonde, Assistant Professor, Degree College of Physical Education, HEPM Amravati, for his inevitable and continuous efforts regarding the workshop. At last but not the least, I would like to thank all the participants offline and online as well for their active participation to make workshop a remark of impact. From here, with the permission of President of Closing Ceremony and Workshop Director, I hereby announce this workshop is concluded here. Thank you, everyone.